In this review video, we'll work through a set of real exam-style Calculus 1 problems on limits and continuity. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos. Just the problem-solving portion for this exam review. So you can stay focused as you prepare for your exam. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. We're given a function f whose graph is given, and we're going to evaluate the following limits. Let me move this up a little bit so that we can see the limits. The first limit that we're going to evaluate is the limit as x goes to -2 from the left of f of x. If we look at our graph and find the point -2, we have to look at what happens to the function as we're to the left of -2 and going towards -2. You can see that our function is going to equal -1. So we say that our limit is equal to -1. Now let's look at part B. For this one, we are also going to take the limit as x goes to -2, but we're going to go from the right of -2. If we look up at our graph, we're going to go along the function as we approach -2 from the right, and you can see that our function value is going to approach 1. So our limit is equal to 1. Now in part C, we're asked to find the limit just as x goes to -2, not from the right or from the left. To find out what this equals, we need to see if the limit from the left is equal to the limit from the right, and we can see that the limit from the left is not equal to the limit from the right, so we say that this limit does not exist, and we write it as d in E. Now let's look at part D. For this one, we're going to take the limit as x goes to +2 from the left. Let's focus on 2 on our graph, and we're going to come from the left, and we can see that the value is going to equal 1. Now for part E, we're going to go back up to our graph, but this time we're going to approach 2 from the right, and we can see that our function is going to equal 2. So let's write that this is equal to 2. For part F, we want to see what the limit as x approaches 2 is equal to. Notice that the left-hand limit and the right-hand limit are not equal, so we say that this limit does not exist. Hopefully you're getting the hang of this. Now let's look at our third set of examples. This is going to be different than the first two that we just looked at. We're first going to look at the limit as x approaches 4, so let's put our eyes here on 4. We're going to look at what happens as we approach 4 from the left. So we're going to go this way, and you can see that our function is going to approach the value 2. So this is equal to 2. Now let's see what happens as we approach from the right. As we approach from the right, our graph has what we call oscillatory behavior, and it oscillates between two values and never settles down. When that happens, we say that our limit does not exist. So let's write d in E, because it's not equal to one value. It just keeps bouncing around between values. Now let's look at I. This is the limit as x approaches 4. So again, we're going to look at the left-hand limit and the right-hand limit, and we're going to notice that they are not the same. So we say that this limit does not exist. Let's now look at two examples so that we can learn how to evaluate infinite limits, because these can be really tricky. In our first example, we have a function f whose graph is given, and we're asked to evaluate the following limits. Let's move this up so we can see our limits. The first limit that we're going to evaluate is the limit as x approaches 2 of f of x. Let's go up here and highlight 2, and then let's look at our function. As x approaches 2 from the left, we go to -infinity, and as it approaches from the right, we also go to -infinity. So this is equal to minus infinity. Let's look at part B. For this one, we're taking the limit as x goes to 5. Let's go up here then and look at 5. And our function from the left goes to infinity, and from the right, it also goes to infinity. So this is equal to infinity. Now let's look at C and D. For both of these limits, x is going to minus 3. So let's go up here and look at that on the graph. From the left, it's going to minus infinity, and from the right, it's going to plus infinity. Let's write that down. So the first one is coming from the left, and it's minus infinity. Second one is coming from the right, and it's plus infinity. Those two limits are different, so we can say for part E that the limit as x goes to minus 3 of f of x does not exist. So we write D, N, E. We have one more part, and this part asks us to find the equations of the vertical asymptotes. I always like to ask students this because I think it's just good practice. Notice that we have a vertical asymptote at minus 3, at 2, and at 5. And we can write the equations for these vertical asymptotes as x is equal to minus 3, x is equal to 2, and x is equal to 5. So just remember, any vertical asymptote can be written as x is equal to some number. Let's now look at our second example, and I think this is the hardest one of the entire section. In part A, we're asked to find the limit as x goes to 2 from the left of the function 4 divided by x minus 2. Whenever you evaluate a limit, the first thing you need to do is use direct substitution and just plug in what x is equal to. This is equal to 4 divided by 2 from the left minus 2. I think it's easiest to evaluate this if we draw a little number line, put a 2 on it, and then put a 2 from the left, and then say, okay, let's let this be equal to 1.99. I just think it's easier to have a concrete number in there. This then becomes 4 over 1.99 minus 2, which is 4 over minus 0.01. Now, that number is going to get a lot smaller as we approach 2 from the left. So it's going to be minus 0.000, lots of zeros, and then a 1. So what we have here is 4 divided by a really, really small number that's negative. So we can write this as 4 divided by 0 from the left. Up here in a box, I wrote down what this equals. If we have 1 and divide it by a really, really small number that's negative, it's going to equal minus infinity. So we can say that this limit is equal to minus infinity. Let's now look at part B. Again, we're going to start by plugging this in. So this is 4 divided by 2 from the right minus 2. We can think of a number 2 to the right as maybe 2.01. And then we subtract 2. So this is 4 divided by 0.01. So this is 4 divided by 0 from the right, just meaning it's really close to 0, but it's positive. And this is equal to positive infinity. I have that formula written up there if you want to memorize it. Now let's look at part C. We're going to begin by plugging in that x is equal to 0 from the right. So we have 0 from the right minus 1, all divided by 0 from the right quantity squared, 0 from the right plus 2. 0 minus 1 is just minus 1. And then 0 from the right squared it's going to be positive, so we write that as 0 from the right. And then 0 from the right plus 2 is just 2. So we have minus 1 on top, and then a 0 that is positive times 2 gives us a 0 from the right. This is going to be equal to minus 1 times 1 over 0 from the right, which is minus 1 times infinity, which is equal to minus infinity. We're going to look at 5 limit examples, and each of these uses a different algebraic technique to evaluate it. Let's look at our first example. The first thing that we always want to do is to just plug in our number and see what we get. So this is 25 minus 5 from the right squared, which is 25, all divided by 5 to the right squared again, so that's 25, minus 10 times 5, which is 50, plus 25. So you can see that this gives us 0 divided by 0, which is an indeterminate form. When we look at this problem, we see that we have a quadratic in the numerator and in the denominator, so that clues us in that we can probably use factoring to evaluate this limit. We will factor the top and then factor the bottom. So we have the limit as x goes to 5 from the right. Factoring the top, we get a 5 minus x and a 5 plus x. Now we can factor the denominator. This is going to be x minus 5 times x minus 5. Let's focus on this term and this term. Those terms are almost the same, they are just different by a negative. So what we can do is we can rewrite the term on the top and take a negative out. Let's write this as the limit as x approaches 5 from the right of minus x minus 5, and then we have a 5 plus x, and then our denominator is the same, x minus 5 and x minus 5. Now let's focus again on these two terms. They are the same now, so we can cancel them out. And we can now go ahead and substitute in that x is going to 5 from the right. This gives us a minus 5 plus 5 from the right, all divided by 5 from the right minus 5. On the top, we have a minus 10. And then in the denominator, we can think of 5 from the right as 5.000, lots of zeros and then a 1, minus 5. So this is a number close to 0, but it's going to be positive. So we have a negative number divided by a really small number that's positive, and that's going to give us an answer of minus infinity. So our limit is equal to minus infinity. Let's now look at our second example. We're going to begin by substituting in that h is equal to 0. This gives us the square root of 1 minus 1, all divided by 0. So we get 0 divided by 0, which we saw up above is an indeterminate form. Often, when we have a limit with a square root, we can evaluate it by multiplying by a conjugate. Let me remind you what a conjugate is. The conjugate of the square root of x minus a is equal to the square root of x plus a. When we multiply it by a conjugate, often terms will cancel out. So that's why we're going to do this. We're going to take the limit as h goes to 0 of the square root of 1 plus h minus 1, all divided by h, and we're going to multiply it by the conjugate. The conjugate is going to be the square root of 1 plus h plus 1. All we're doing is changing this sign. And then we can't change the problem, so whatever we multiply on the top, we have to multiply on the bottom because we can really just be multiplying by 1. Otherwise, we would change the problem. Now let's go ahead and multiply this out. This is the limit as h goes to 0. Let's use the FOIL method and multiply the first terms. So that's root 1 plus h times root 1 plus h. So that gives us a 1 plus h. Now let's multiply the outer terms. So we're multiplying square root of 1 plus h plus 1. So that gives us square root of 1 plus h. Now we're going to multiply the inner terms, and that gives us a minus square root of 1 plus h. And then lastly, we'll multiply the last terms, and that's going to give us a minus 1. And our denominator looks like h times the square root 1 plus h plus 1. Notice that I did not multiply out the denominator. It's always good to hold off not multiplying out the term that doesn't have the two conjugates in it. Now let's see what cancels. This term is going to cancel with this term, and our 1 is going to cancel with our 1. So we have the limit as h goes to 0 of just h on top, and then we have an h in the denominator and a square root of 1 plus h plus 1. Now you can see that our h's cancel, and that's why I didn't multiply things out. And we can now just go ahead and plug in h as 0. We have a 1 on the top. That comes from our h canceling. And then we have the square root of 1 plus 0 plus 1. So this just gives us an answer of 1 divided by 2. And that's what our limit is equal to. Let's now look at our third example. We'll start by substituting in what x is. This gives us 1 all divided by 0 times the square root of 1 minus 1 over 0. This gives us 1 over 0 minus 1 over 0, and that's infinity minus infinity. And just like 0 divided by 0, this is also an indeterminate form. When you have a limit that equals infinity minus infinity, it comes from having two terms, and we can often evaluate a limit like that by combining the two terms and getting a common denominator. So let's go ahead and let's do that. We're going to get a common denominator equal to x times the square root of 1 plus x. We have the limit as x goes to 0. Let's write our denominator first. We have x square root 1 plus x. On the left, we have a 1. And for our term on the right, we only have an x. So we need a square root of 1 plus x. So we're going to subtract square root 1 plus x. Now let's go ahead and plug in x is equal to 0. So we have 1 minus the square root of 1 on the top, and we have 0 times the square root of 1 on the bottom, and that gives us 0 divided by 0, which is our indeterminate form that we looked at for our first and second examples. Notice now that we have a term in the top that's a number minus a square root. That means that we can multiply by a conjugate. Let's go ahead and let's do that. This is the limit as x goes to 0, 1 minus the square root of 1 plus x, all divided by x square root of 1 plus x, and let's multiply by the conjugate, 1 plus square root of 1 plus x, all divided by 1 plus square root of 1 plus x. If I were teaching this in class right now, I would start to get a lot of moans. I know this is a long problem, but hang with me. You can do this. Let's multiply out our top. We'll use the FOIL method. We'll multiply the first, which is 1. We'll multiply the outer terms, which gives us a plus square root 1 plus x. We'll multiply the inner terms, which is minus square root of 1 plus x. And then the last terms, which gives us a minus, and then the square roots combine to be a 1 plus x. And then our denominator, we just have to copy down x square root 1 plus x. Do not multiply the denominator out because we're hoping that terms are going to cancel. Let's look back up at our numerator and we'll cross out the terms that cancel. We have this term and this term cancel, and then our ones cancel. So let's go ahead and rewrite this as the limit as x goes to 0. We have a minus x up top, and then down below we have an x, square root of 1 plus x, 1 plus square root 1 plus x. Our x's cancel, which is why we did not multiply out the denominator. And now we can go ahead and plug in x is 0. So up top we get a minus 1. And then in our denominator we have square root of 1. And then we have a 1 plus square root of 1. So this is minus 1, all divided by 2. And that's the value of our limit. Remember that in this example, we used two techniques. We got a common denominator, and then we multiplied by a conjugate. Let's look at our fourth example. This one isn't as bad as our third one. Let's start by plugging in h is equal to 0. This gives us a 2 plus 0 cubed minus 8, all divided by 0. So this is 8 minus 8 over 0, which is 0 over 0, which is an indeterminate form. Notice in this problem that we have 2 plus h raised to the third power. Whenever you have a limit with an expression raised to a power, you can often evaluate it by multiplying out that power and then hoping that some terms cancel. We're going to begin by multiplying out 2 plus h cubed. You may not remember that formula, so let me go ahead and let's write it down. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. If you don't want to remember that formula, you can just multiply 2 plus h cubed out by hand. I'm going to use the formula, so I'm going to write down this is the limit as h goes to 0, 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed. And then we can't forget we have a minus 8 to tag on there. All of this gets divided by h. Now let's go ahead and let's simplify. This is the limit as h goes to 0. We have an 8 plus 4 times 3 is 12, so we have a 12h plus 6h squared plus h cubed minus 8, all divided by h. Now let's look at our terms that cancel. We have an 8 that cancels, so that's great. Notice in the numerator that we have an h common to every term. So I am going to factor out an h, and we'll write this as the limit as h goes to 0. We'll pull out an h, and we have a 12 plus 6h plus h squared, all divided by h. Now you can see that our h's cancel, and we can just go ahead and substitute in that h is going to 0. This gives us 12 plus 0 plus 0, so our limit is equal to 12. Let's now look at our last limit example. This is equal to the absolute value of minus 4 plus 4, all divided by minus 4 plus 4. So this is the absolute value of 0 divided by 0, and we end up with our indeterminate form, 0 divided by 0. Notice in this limit that we have an absolute value function. Whenever you have a limit with an absolute value function, The best thing to do to evaluate it is to break up that absolute value function into pieces. Just as a review, the absolute value of x is equal to positive x when x is greater than or equal to 0, and minus x when x is less than 0. We're going to use this as a model to find out what the absolute value of x plus 4 is equal to. It's just going to be equal to x plus 4 when x plus 4 is greater than or equal to 0, and then minus x plus 4 when x plus 4 is less than 0. Let's now see what this piece is equal to. Let's bring the 4 to the right. So this is just x is greater than or equal to minus 4. And then this piece is x is less than minus 4. I'm going to highlight these because we're going to need that. We're going to break up this limit into our left-hand piece and then our right-hand piece. Let's look at the limit as x approaches minus 4 from the left. That's going to be this piece right here because x is less than minus 4. So we're going to substitute in for our numerator minus the quantity x plus 4. So we have a minus x plus 4 on top. And then down below, we have an x plus 4. These terms cancel. So we're left with a value of minus 1. Now let's look at our right-hand piece. This is the limit as x goes to minus 4 from the right. We're going to plug in x plus 4. So we have an x plus 4 on the top, x plus 4 on the bottom, and we end up with a value of 1. Notice that our limit from the left does not equal our limit from the right. We know from the definition of a limit that it's only going to exist if the limit from the left equals the limit from the right. So we can conclude that the limit as x goes to minus 4 of absolute value x plus 4 all divided by x plus 4 does not exist. So we're going to write this as DNE for our answer. In our first example, we are given that f of x lies between 3x and x cubed plus 2 when x is between 0 and 2, and we want to evaluate the limit of f of x as x goes to 1. I think the hardest part of doing these types of limits is to figure out where to start. I always tell students, let's start with what we are given. We are given this expression, 3x is less than or equal to f of x is less than or equal to x cubed plus 2. So that's a good place to start. Now let's look at what we want to find. We want to find the limit as x goes to 1 of f of x. So we'll take the limit as x goes to 1 of all three of these functions. We have the limit as x goes to 1 of 3x less than or equal to the limit x goes to 1 of f of x less than or equal to the limit x goes to 1 of x cubed plus 2. This, in the middle, is what we want to find, so let's evaluate the left-hand limit and the right-hand limit. All we have to do is substitute in that x is going to 1. So on the left, we have 3 times 1 less than or equal to the limit x goes to 1 of f of x less than or equal to plugging in 1. We have 1 cubed plus 2. So we see that on the left, we have a 3. And on the right, we also have a 3. We can use the squeeze theorem then to conclude that the limit as x goes to 1 of f of x is equal to 3. Let's now look at an example. In part A, we are going to state the values of x at which our function f is discontinuous and then explain why. In part B, at those numbers where our function is discontinuous, we are going to determine whether our function is continuous from the right, from the left, or neither. A function can be discontinuous at a point, but still be continuous at that point from the left or from the right. Let's see how this works. We'll begin with part A. Let's start by looking at our x values as we go from left to right. Here's the first x value that we're going to look at. If you look up at our graph, notice that our function value has an open circle at that point, and that means our function is discontinuous. So we're going to say that at x is equal to minus 4, f of minus 4 is undefined. And that's why our function is discontinuous. Let's now look at x is equal to minus 2. At this point, our function value exists. However, the limit from the left does not equal the limit from the right. So let's go down here and let's write x is equal to minus 2. The limit as x approaches minus 2 of f of x does not exist. Now let's go to our next point. That's going to be the point 2. At this point, our function value exists, but again, the limit from the left does not equal the limit from the right. So it's discontinuous at that point. We'll write down x is equal to 2. The limit as x approaches 2 of f of x does not exist. Let's now look at our last point. That is x is equal to 4. For this point, our function exists. However, the limit from the left does not equal the limit from the right. So we'll write down x is equal to 4. The limit as x goes to 4 of f of x does not exist. Sometimes you can write does not exist as D and E, and that will make things a little bit quicker. Let's now go to part B. We'll pull this up so we can see. For part B, we wanted to know at these numbers, that's minus 4, minus 2, 2, and 4, if f is continuous from the right or from the left or neither. We'll see if we can squish B in right here. So at x is equal to negative 4, we need to look at our function. Because there is an open circle at that point and no closed circle, our function is not continuous from the left or from the right. So we're going to write down neither. Let's look at our next point. X is equal to minus 2. At minus 2, let's go up here and look at our graph. Notice that as we approach from the left, our left-hand limit is equal to our function value, so it is continuous from the left. So let's go down here and let's write left. Now we go to x is equal to 2. Let's go back up to our graph and look at 2. Our function value is defined here. This limit is equal to the function value, so it is continuous from the right. So we'll put right down here. And then our last one, x is equal to 4. Let's go up here and look at our graph and see what's going on at 4. Here's our function value, and the limit that is equal to it is the one coming from the right. So just like x is equal to 2, at x is equal to 4, our function is continuous from the right. I hope this makes this problem clear. I know when I used to teach this problem in class, this was one that students really struggled with and had to go over a couple of times. We're going to now look at some examples where we are going to state where our function is discontinuous and then state the type of discontinuity. In our first example, we are going to be looking at this graph. There is a lot to that graph. I think the best way to approach this problem is to start looking at this graph and see where it is discontinuous, and we'll start looking at the points on the left and then move to the points on the right. The first point that we're going to look at is x is equal to minus 2. At x is equal to minus 2, the function exists and the limit exists. However, these two values are not the same. So we're going to say that at x is equal to minus 2, we have what's called a removable discontinuity. It is not a jump discontinuity because when we have a jump discontinuity, the value starts at one value, goes to the next value, and then continues on from that value. With this one, our function only jumps at a single point. So it's called a removable discontinuity. Let's now look at our next x value, and that is x is equal to 2. Notice at x is equal to 2, our function is defined. However, the limit from the left is different than the limit from the right. And that tells us that we have a jump discontinuity. At x is equal to 2, let's write down that we have a jump discontinuity. Now let's look at what's happening when x is equal to 4. Our function is not defined at x is equal to 4, and our limit from the left is going to infinity, and our limit from the right is going to infinity. So at x is equal to 4, we have what's called an infinite discontinuity. Now let's look at our last point. That is at point 6. You might want to pause the video and see if you can determine what type of discontinuity we have here. Our function is defined at x is equal to 6, but the limit from the left does not equal the limit from the right. And that means just like when x is equal to 2, we have a jump discontinuity. So we'll write down x is equal to 6. We have a jump discontinuity. Let's now look at our second example. In our second example, we see that the function is defined at x is equal to 1. And to determine the type of discontinuity, we need to understand better what's happening in the region around x is equal to 1. So let's look at the limit as x approaches 1 from the left of 1 over x minus 1. This is approximately 1 divided by 1 from the left minus 1. So this is approximately 1 divided by a number like 0.99 minus 1. So this is going to be 0 from the left, and that's going to be minus infinity. Now let's look at the limit as x approaches 1 from the right. This one's easier. This is 1 over x minus 1. This is approximately 1 divided by 1 from the right minus 1. Think of this as 1.0001 minus 1. So this is 1 divided by 0 from the right. And this is positive infinity. Because our limits are infinite, we have an infinite discontinuity at x is equal to 1. So let's write down infinite
discontinuity, we're just going to abbreviate that, at x is equal to 1. Let's go ahead and let's graph this just so that we can better understand it and see what it looks like. We have an infinite discontinuity at x is equal to 1, so we'll put a vertical asymptote there. And then at 1, our function is equal to 2, so we'll put a closed circle here. As we approach 1 from the left, we're going down to negative infinity. So our function's going to look like this. And as we approach 1 from the right, it's going to go up to positive infinity. Later on in this course, we're going to be talking about horizontal asymptotes, which we really need, honestly, to be able to understand this graph a little bit better. But for now, I just wanted you to see the graph so that you can see what it looks like when we have an infinite discontinuity. Let's now look at example 3. This one is a little bit more complicated, but just like our second example, our function is defined at x is equal to 1, and now we have to figure out what's going on at a region near 1. Let's take our complicated function when x is not equal to 1 and see if we can maybe factor it. Let's take x squared minus x, all divided by x squared minus 1. We can definitely factor it. In the top, let's pull out an x, so we have an x minus 1. And in the denominator, we can factor that as x plus 1 and x minus 1. Now let's notice that these two terms cancel out, and we can write this as x all divided by x plus 1. Because we canceled out an x minus 1, what we can do is we can take x minus 1, set it equal to 0, and solve for x, and we get x is equal to 1. This means at x is equal to 1, we have what's called a removable discontinuity because we were able to remove that from our function. Now let's look at the function that we have left. Notice that there's an x plus 1 in the denominator. Let's take that and let's set that equal to 0. And that gives us x is equal to minus 1. When x is equal to minus 1, our denominator is going to go to 0. So our function is going to go to infinity and also to minus infinity. Let's go down here to the bottom and write down then at x is equal to negative 1, we have an infinite discontinuity. And I'm going to go ahead and I'm going to highlight these answers. We have a removable at x is equal to 1, and we have an infinite discontinuity at x is equal to minus 1. Let's go ahead and let's graph this function just so that we can better understand this. At negative 1, we have an infinite. So that means we're going to have an asymptote there. Our function actually has a horizontal asymptote at y is equal to 1. Again, there's no way that you would know that at this point. Just take my word for it. And then we have on the right-hand side of our asymptote, our function's going to go down like this. It does pass through the origin, and it's going to go over like this. And then at x is equal to 1, it's defined to be 1, so we're going to put a closed circle there. And we're going to put an open circle right there. So you can see from the graph, we have an infinite discontinuity at x is equal to minus 1 and a removable discontinuity at x is equal to 1. We're going to now look at an example where we're asked to find the value of a constant c that makes f of x continuous everywhere. The first piece of our function and the second piece of our function are both polynomials, which means they are going to be continuous everywhere. If our function is going to be discontinuous, it is going to be discontinuous at x is equal to 3. Now, I think what we can do is find a value of c where it is not discontinuous. In order to do that, what we're going to have to do is we are going to have to set the first piece of the function equal to the second piece of the function and plug in x is equal to 3. Let's go ahead and let's do that. We have c times 3 cubed minus 6 is equal to 4 times 3 squared plus 2c times 3. Now we have to solve for c. Let's clean this up a little bit. On the left, we have 27c minus 6. And on the right, we have 3 squared, which is 9, times 4 is 36, plus 2 times 3 is 6, so we have a 6c. Let's move the c's to the left and the constants to the right. So we have 27c minus 6c on the left and 36 plus 6 on the right. 27 minus 6 is 21, so we have 21c is equal to 36 plus 6, which is 42, and that works out real nice. Dividing by 21, we see that c is equal to 2. So we can conclude that our function is going to be continuous even at x is equal to 3 if c is equal to 2. We're going to look at some examples and we are going to determine the intervals on which our function is continuous. Let's look at our first example. Notice that we have a denominator equal to x plus 1. Our function is not going to be continuous when that denominator is equal to 0. So let's take x plus 1 and let's set it equal to 0, and we get x is equal to negative 1. So our function is not going to be continuous at x is equal to negative 1. The trigonometric function sine x is always continuous. Now what we need to do is find the intervals on which our function is continuous. I think the easiest way to do that is to just draw a number line. We'll label this as x, and we're going to take x is equal to negative 1, and we're going to put a big X right there. X cannot be equal to negative 1. So the intervals on which our function is continuous are going to be from here to here, and then from here to here. So our solution is our function is continuous on the intervals minus infinity to minus 1, union minus 1 to infinity. Now let's look at our second example. We're going to focus on our square root. We talked up above about our square root being only defined when what is inside the square root is greater than or equal to 0. So we are going to set x minus 4 greater than or equal to 0. So we get x is greater than or equal to 4. The other piece of our function is a polynomial, and it is always continuous. Let's go ahead now and let's do our number line. We'll label it as x. We're going to put the point 4 here, and we're going to denote that x has to be greater than or equal to 4. So we're going to put a square bracket here and an open bracket over there at infinity. Our answer then is our function will be continuous on the interval from 4 to infinity, and we have a closed bracket at 4. Now let's look at our third example. We'll look at our natural log function first. A natural log is only defined if what is inside the natural log is greater than 0. So we're going to set x minus 1 greater than 0, and that's going to give us that x has to be greater than 1. Now let's look at our denominator. We cannot have a denominator be equal to 0, so we're going to require that x squared minus 4 is not equal to 0. Solving this, we get x squared is not equal to 4, which means x is not equal to plus or minus 2. Don't forget the negative piece. Now let's go ahead and let's draw our number line. We're going to have more to put on this one. Let's see here. Let's put the point 1. And then we're going to put the point minus 2 and 2. Now let's see what's going on here. X cannot equal -2 or +2, and then x has to be greater than 1. So we're going to put an open bracket here. It can't equal 2, so we're going to put open brackets around 2 and then a bracket here at infinity. So our answer is that our function is continuous on the interval from 1 to 2, union 2 to infinity. One really nice application of the intermediate value theorem is when we can use it to show that an equation has a root in a specified interval. And that's what our examples are going to be about. In our first example, we are going to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Let's talk at first about what a root is. A root of this equation is just a point x where x cubed minus x minus 2 is equal to 0. So basically, when we solve this equation, we are just finding the roots. I have graphed this equation so that we can better understand this. What we are looking for is to show that we have a root of this equation. So that is going to be this point right here where our function x cubed minus x minus 2 is equal to 0. And we want to show that we have a root between x is equal to 1 and x is equal to 2. To show this, we are going to look at our function values at 1 and at 2. F at 1 is equal to 1 cubed minus 1 minus 2, which is just minus 2. And let's make a note that that's less than 0. And then f of 2 is 2 cubed minus 2 minus 2, which is 8 minus 4, is equal to 4, which is greater than 0. Because f of 1 is less than 0 and f of 2 is greater than 0, the intermediate value theorem tells us that there has to be a number c such that f of c is equal to 0, because our function has to take on every value between -2 and 4, and 0 lies between -2 and 4. So by showing that f of 1 is less than 0 and f of 2 is greater than 0, we've basically shown that the intermediate value theorem will guarantee that we have a root between 1 and 2. In these examples, we're asked to find the limit. In our first example, we're taking the limit of 4x minus 3 divided by 2x minus 1 as x goes to infinity. Whenever you evaluate a limit, the first thing that you want to do is substitute in what your value x is going to. So let's go ahead and let's do this. X is going to infinity. So we have 4 times infinity minus 3, all divided by 2 times infinity minus 1. 4 times infinity is going to be a lot bigger than minus 3. So I'm going to write that the top is equal to infinity. And then the same thing happens with the denominator. 2 times infinity is a lot bigger than minus 1, so we can write this as infinity, and we get the indeterminate form infinity divided by infinity. What we're going to do now is divide the numerator and the denominator by the highest power of x in the denominator. This power of x is right there, so we're just going to divide the top and bottom by x. This gives us the limit as x goes to infinity. We're going to take the top part and divide it by x, and then do the same thing for the bottom part. Now we'll go ahead and break it up into pieces. So we have the limit as x goes to infinity. 4x divided by x is just 4, and then we have a minus 3 over x. And in the denominator, we have 2x divided by x, so that's just going to be 2 minus 1 over x. Now we can go ahead and plug in that x is approaching infinity. So this is 4 minus 3 divided by infinity, all divided by 2 minus 1 over infinity. This term is going to go to 0, and this term is going to go to 0. So we're left with 4 divided by 2, which is 2. So 2 is the value of our limit. Let's now look at our second example. This one is a lot harder than the first one. We're going to begin just like we did with the first one, and we're going to substitute in that x is going to plus or minus infinity. This is equal to the square root of 2 plus or minus infinity squared plus 1, all divided by 5 times plus or minus infinity minus 3. Let's look at the numerator first. The biggest term is the first one, 2 times infinity squared. So let's just write this as the square root of infinity squared, all divided by 5 times plus or minus infinity minus 3. The minus 3 won't matter, so we can just write this as plus or minus infinity. So we end up with some form of infinity divided by infinity, which is an indeterminate form. Now what we're going to do is divide the numerator and the denominator by the highest power of x in the denominator, and that's just going to be x. This is equal to the limit as x goes to plus or minus infinity, the square root 2x squared plus 1 divided by x, all divided by 5x minus 3 divided by x. This is actually more complicated than it looks. We need to know how to divide a square root function by x. To figure out how to do this, let's look at the definition of the square root of x squared. You may or may not have seen this before. The square root of x squared is defined to be the absolute value of x, and we know absolute value of x is x when x is greater than or equal to 0, or minus x when x is less than 0. This tells us as x approaches positive infinity, the square root of x squared is going to equal x. And then as x goes to minus infinity, we're going to look at the other piece, and we can write down that the square root of x squared is equal to minus x. Now let's apply this to our limit. Notice that we have a different value as x goes to infinity and as x goes to minus infinity. This means that we're going to have to look at our limits separately. Our first limit is the limit as x goes to infinity, square root 2x squared plus 1, all divided by 5x minus 3. Now we're going to divide the top and bottom by x. So this is the limit. X goes to infinity, square root 2x squared plus 1. Here, we're going to divide by the square root of x squared because x is going to infinity. And then on the bottom, we're just going to divide by x. This gives us the limit as x goes to infinity of the square root. Pulling in x squared, we have 2x squared divided by x squared is just 2. And then we have a plus 1 over x squared. And in the denominator, 5x divided by x gives us 5 minus 3 divided by x. Now, as x goes to infinity, this piece and this piece are going to go to 0. So what we have left as an answer is the square root of 2 divided by 5. Let's go ahead and let's highlight that. Now we're going to look at the limit as we approach minus infinity. This is the square root 2x squared plus 1, all divided by 5x minus 3. Hang with me. I know my students, when I used to teach this in class, felt like this was one of the hardest problems they've done. Since x is going to minus infinity, looking over to the right, we can see from this right here that x is equal to minus square root of x squared. So that's what we're going to divide by. In the numerator, we have 2x squared plus 1, and we're going to divide by minus square root x squared. And then on the bottom, we're just going to divide by x. So we have 5x minus 3 divided by x. I'm going to go down here to the lower left. We're kind of running out of space. Let's rewrite this as the limit. X goes to minus infinity. Do you see this minus sign right there? We are going to take that out in front. So we have minus square root. Now we can take the x squared inside the other square root, and this becomes 2 plus 1 over x squared, just dividing everything. And then in the denominator, we have 5 minus 3 over x. As x goes to minus infinity, this term and this term are going to go to 0, and we're left with an answer of minus square root of 2, all divided by 5. In these examples, we are going to find the limit. Let's look at our first one. The first thing we're going to do is plug in that x is going to infinity. So this is infinity squared minus infinity. And this is called the indeterminate form, infinity minus infinity. What we're going to have to do now is look at our function, x squared minus x, and figure out how to simplify that. When I look at that function, I see that there is an x common to both terms. So let's start by factoring out an x. This becomes the limit as x goes to infinity, x times x minus 1. Now let's go ahead and let's plug in that x is going to infinity, and we have infinity times infinity minus 1. So that's just equal to infinity. And that's actually what our limit is equal to. This is an example of a limit that does not exist, but if you can say that the limit is infinity, that is better than just saying it doesn't exist. This just gives us a little bit more information about the behavior of the limit. Let's now look at our second example. Again, we're going to start by plugging in that x is going to infinity. So we have the square root of infinity to the fourth plus 6 times infinity squared minus infinity squared. This is equal to the square root of infinity to the fourth. We're going to ignore the 6 infinity squared because it's a lot smaller compared to the infinity to the fourth. And then we subtract infinity squared. But the square root of infinity to the fourth is like infinity squared. So this is really the indeterminate form infinity minus infinity. Now we have to figure out how to evaluate this. When I look at our function, notice that it has a square root and then it's subtracting something after the square root. That tells us that we should probably multiply by the conjugate. The conjugate of the square root of a minus b is the square root of a plus b. So that's what we're going to multiply by. This is equal to the limit as x goes to infinity, the square root x to the fourth plus 6x squared minus x squared, and we're going to multiply by the conjugate. So we have the square root x to the fourth plus 6x squared plus x squared. We're just changing the sign. Now, this is really important. We can't change the limit. So if we multiply by the conjugate, we also have to divide by that same thing. X to the fourth plus 6x squared plus x squared. Doing it this way, it's like multiplying by 1, and we don't change the problem. Now let's go ahead and let's multiply things out. Just to make it easier, I'm going to use the FOIL method. So we're going to multiply the first terms. That's both of the square roots, and they multiply out to be x to the fourth plus 6x squared. And now we're going to multiply the outer terms. That is the square root x to the fourth plus 6x squared times x squared. Now let's multiply the inner terms. I'm going to go ahead and put parentheses up here to make it easier. The inner term is minus x squared times the square root of x to the fourth plus 6x squared. And then finally our last terms, which is our x squared terms multiplied, which is minus x to the fourth. Now we're going to divide all of this by the square root x to the fourth plus 6x squared plus x squared. Now the nice thing about multiplying by a conjugate is that things cancel. Let's go ahead and let's see what cancels. Our x to the fourth is going to cancel. And then this term is going to cancel with this term. And we only have one term left on top. Let's go ahead and let's write that down. This is the limit as x goes to infinity, 6x squared, all divided by square root of x to the fourth plus 6x squared plus x squared. Now what we're going to do is we're going to have to plug in infinity again and see what we get. When we plug in infinity, on the top, we're going to get infinity, and on the bottom, we're going to get infinity. So now we have another indeterminate form, infinity divided by infinity. We just talked about this form, so we know exactly what to do. We are going to have to divide by the highest power of x in the denominator. And that's going to be x squared, which is the same thing as the square root of x to the fourth. So we're going to divide the top and the bottom by x squared. So we have the limit as x goes to infinity, 6x squared divided by x squared, all divided by the square root x to the fourth plus 6x squared. That all gets divided by x squared, and then we have an x squared that gets divided by x squared. Let's see what this is. On the top, our x squares are going to cancel, and we're just going to have a 6. In the denominator, we're going to bring in the x squared as an x to the fourth. So this is x to the fourth plus 6x squared, all divided by x to the fourth. And then we have a plus 1. Hang with me, we're almost done. We have one more step to do. On the top, we have a 6. Now we're going to divide out this x to the fourth. This is going to give us a 1 plus 6 over x squared plus 1. Now we can go ahead and plug in. X is going to go to infinity. So this term is going to go to 0, and we have a 6 all divided by the square root of 1 plus 1. So this is 6 divided by 2, which is equal to 3. So our limit is equal to 3. I've graphed this function down here at the bottom so that you can see that as x gets really large or really small, our function is going to go to the value of 3. Notice in the graph that there is also a horizontal asymptote at y is equal to 3. Limits at infinity lead to horizontal asymptotes, and that's exactly what we're going to look at next. Let's look at some examples where we are going to find the horizontal and vertical asymptotes of the curve. Our first curve is defined as y is equal to 4x minus 3 divided by 2x minus 1. Let's first find our horizontal asymptote.
Since the power of x is the same in the numerator and the denominator, we can look at the limits as x goes to plus infinity and as x goes to minus infinity at the same time. The limit as x goes to plus or minus infinity of 4x minus 3, all divided by 2x minus 1, is equal to plus or minus infinity divided by plus or minus infinity. So we can just think of this as the indeterminate form, infinity divided by infinity. Since we have the indeterminate form, infinity divided by infinity, to evaluate this limit, what we're going to do is to divide the numerator and the denominator by the highest power of x in the denominator, which is just x. We'll write this then as the limit as x goes to plus or minus infinity, 4x minus 3 divided by x, all divided by 2x minus 1 divided by x. This is just the limit as x goes to plus or minus infinity. 4x divided by x is just 4. So we have a 4 minus 3 divided by x. And in the denominator, we have a 2 minus 1 divided by x. 3 divided by x and 1 divided by x are going to go to 0 as x goes to plus or minus infinity. So we just have 4 divided by 2, which gives us a limit value equal to 2. And our asymptote is y is equal to 2. Let's now look at our vertical asymptotes. To find a vertical asymptote, what you have to do is set the denominator equal to 0. Our denominator is 2x minus 1, so we're going to set that equal to 0, and then we'll solve for x, and we get x is 1/2. And that is our vertical asymptote. I've graphed this function so that you can see that the horizontal asymptote is indeed y is equal to 2, and the vertical asymptote is given by x is equal to 1/2. Let's now look at our second example. This example is a bit more complicated than the first one. We're going to begin again by looking at the horizontal asymptote first. Since the numerator and the denominator contain different powers of x for their leading terms, and they're both not even powers, we need to look at the limits as x goes to infinity and x goes to minus infinity separately. Let's begin by looking at the limit as x goes to positive infinity. We're going to divide both the numerator and the denominator by the highest power of x in the denominator, and that's going to be x squared. Let's plug in x to see what we get. On the top, we have infinity cubed minus infinity, and then on the bottom, we have infinity squared minus 6 times infinity plus 5. So what we have on the top is infinity cubed, because that's much bigger than infinity. And then on the bottom, we can write this as infinity squared. That's the highest power. So this is going to equal infinity. Now, you can take a more algebraic approach to solving this and divide both the numerator and the denominator by the highest power of x, and you'll get the same answer. Let me just go ahead and do that so you can see. Honestly, sometimes it just depends what your instructor is asking for, which way you have to do it. We're dividing the top and the bottom by x squared, so this is 1 minus 6 over x plus 5 over x squared. This term goes to 0, as does this term and this term. So we're left with the limit as x goes to infinity of x, which is just infinity. And that matches what we got earlier. Now let's look at what happens as x approaches minus infinity.
We have x cubed minus x, all divided by x squared minus 6x plus 5. Let's plug in x goes to minus infinity. We'll have to watch our negatives here. We have minus infinity cubed minus infinity, all divided by minus infinity squared minus 6 times minus infinity plus 5. These two terms are our largest terms, so we can ignore all the other ones. And this gives us a minus infinity cubed divided by infinity squared, which gives us minus infinity. So that's our answer. Again, you can get that answer by dividing both the top and the bottom by x squared. Now let's think about what our answer tells us. We found that the limit as x approaches infinity and minus infinity is infinity and minus infinity. That tells us that we actually have no horizontal asymptote. Let's now look at our vertical asymptotes. To find the vertical asymptote, we have to set the denominator equal to 0, but there's a catch. We can only do that after we factor out terms that are common to both the numerator and the denominator. So we're going to have to start by factoring the numerator and the denominator. We have x cubed minus x, all divided by x squared minus 6x plus 5. In the numerator, we can pull out an x, so that leaves us x squared minus 1. And then in the denominator, we can factor this as x minus 1 and x minus 5. Notice that in the numerator, we still have a term that needs to be factored, so let's do that. That's x. X squared minus 1 factors into x plus 1 and x minus 1, and then we'll copy down the denominator, x minus 1, x minus 5, and now we can cross out the terms that are common to both the top and the bottom. What we do next is we take the term in the denominator that's left and we set that equal to 0. And that is x is equal to 5, and that is our vertical asymptote. I graphed this function so that you can see that it has a vertical asymptote at x is equal to 5. And I also wanted you to notice one other thing. Do you see this open circle right here? That is called a removable discontinuity. And it happens when you have a function where you can factor out a term such as x minus 1. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.